And now it is my pleasure to introduce Maria Michalska from currently at the ICMC at the University of São Paulo in São Carlos. And she will speak to us about the stability of multiplicity and degree with respect to sublevel sets.
Hello everybody. I'm really glad to be able to talk here today. Thanks for the introduction. Okay, so, I hope it's generic enough, this results for the conference, which is called Generic Geometry. And, okay, so, like, since it might be a little not in the center of your interests, I'm going to speak somehow slowly, present examples, because I think that the subject I'm talking about is kind of interesting. Maybe at the end of the talk I'm going to talk about some applications and why is it more interesting than just being interesting as a problem itself, at least for me. First of all, this is a strictly real problem. So this is over the reals and we're going to stick to this. Okay, so from viewpoint of applications, let's say, the following problems, I'm going to state it in this way. The following is going to be the interesting thing. So we're going to always fix a set S in Rn, and S not necessarily, but throughout the talk it's going to be easier to say that S is semi-algebraic. Okay, yes?
Use black?
Yes, I can use black, yes. Yes, okay. So, usually the set I'm going to consider is S. Okay, so the questions I'm going to address is going to be what polynomials are bounded on S, meaning, well, for which f or such that there exists a constant, of course, such that f is less than the constant on the set S. And the other one is, let's say, what is the structure and behavior of BDS, of the modules, and I'm going to say what's a BDS. It's a module of all the polynomials such that they behave as polynomials of degree D on S. I could substitute here with any polynomial, but let's say it just behaves like a generic polynomial of degree D on the set S. So since we've decided to, these are, let's say, the main questions, I'm going to go a little around to them, and I'm going to define something which is going to be central to my talk, the degree with respect to a set of a polynomial. And it's just the, okay, I'm going to put inf here, A over B. So this is somehow, this is the, let's say, the degree which is, which might be rational. If you want to retrieve a normal degree, you just take the interior part of this, integer part, sorry. F to B is bounded on S. Okay, so this is, let's say, the main definition. Then, let's say these BDS, these modules, are just the F such that its degree with respect to the set F the set S is less or equal D. You can just and by this I mean the integer part plus 1 of rational. Okay, so let me remark, well, as I said, I will go, let's say, slowly and easily. So simple remarks are that B0 of S is always an R algebra, because B0 means that here is 0, meaning that just you have constants. So this means that B0 is the algebra of bounded polynomials on a set. So if you add two polynomials which are bounded, they're going to be bounded. If you multiply two polynomials which are bounded, they're going to be bounded. Plus, plus this is also integrally closed, because the root of an expression where everything is bounded is also going to be bounded. Okay, all the BDs is always a B0S module, so also an R module. And that's maybe all for this moment. Let's just look at the simple examples. What happens on the real line? We have only two cases. Well, never mind whether S is bounded or not. Never mind whether S is semi-algebraic. If S is bounded, then what happens? On a bounded set, every polynomial is bounded. Therefore, all the BD of S, they just behave, well, they are all already the ring of the polynomials. If S is unbounded set, then the BDs, the degree, behaves exactly like the normal degree. So this is exactly like the polynomials of degree not more than D. So let's say the case of the real line is the easiest one and the least interesting one. And so just a remark, from now on I'm going to always assume n is greater or equal than 2, just to get rid of these trivial cases. So let's see some examples where it starts being interesting on the real plane. So there is no general rule like this. Of course, there is a rule that always, if you have a bounded set, everything is bounded on this bounded set. So we already have always this, that for any D, this is already the set of all polynomials. Therefore, also it's interesting to remark that I'm going to stick to S being unbounded. Okay, so in R2, with unbounded sets, there is no general way of saying. Like, for example, if a set contains a cone, it behaves like with a cone. It's almost it has enough so that it behaves exactly like the degree. Only when it becomes finite infinity, it becomes more interesting. So somehow it's the singularities at infinity that are going to contribute to the behavior of the modules. Okay, so what examples I wanted to show, like maybe example 1. Yeah, it's going to come throughout the talk because it's simple. So this is just xy less or equal than 1. So the set is something like this, a simple one. And we can see that, of course, this polynomial in itself is bounded. And in fact, one can show that the bounded polynomials are exactly of this form. And the degree of any polynomial with respect to this set is equal to the, well, let's say the maximum divergence from being a monomial of this sort. So it means like the biggest, like you always take out from any monomial the most xy's you can, and you see like what's the difference there, and you take the maximum. This is the degree. So it somehow behaves like you can see how it diverges from being a polynomial in xy. Okay, a second example. Let's say, is these are somehow examples to keep in mind. Just x equals 0, and here we had a set that had non-empty interior. Here we have a set which is an algebraic set. The behavior is very different in such a case. In such a case, the bounded polynomials are not finitely generated. And I think, well, it's possible for you to see how the degree in general behaves on such a set. Well, this is supposed to be the set. In general, like with those sets which have empty interior, which are really like subsets of algebraic sets, it's really hard because there is this, this behavior that even the simplest brick that we have behaves very abnormally. It's always not finitely generated. In fact, you can show that, which, well, I have shown, and also Plaumann and Scheiderer, that this is true in any dimension, that if S is, well, how this is subset of proper algebraic set, then B0 of S is not finitely generated as an algebra. So also somehow it's more interesting to look at not only like, okay, dimension bigger than 2 as unbounded, but also it's more interesting to look, or yeah, somehow more interesting to look at the sets that have non-empty interior at infinity. Okay, so I'm going to erase a little and just so the examples are here. Just maybe some, so I just wanted to say, maybe I'm going to say in a moment about the results, but also that anytime during the talk, like we're going to look at the sets at infinity. This is what is interesting. Anything that happens in the compact part is not interesting. So whenever I'm going to say that something is Zariski closed at infinity, etc., it means that I'm considering the germ at infinity of the set, meaning outside an arbitrarily compact set. So just if somebody... Okay, I wanted maybe to say something about the relation to the leading term, that there is none. Just you can look at this example and see that you can produce polynomials that the leading term is bounded, but the polynomial is not bounded on this set, and also that the leading term, like after moving a little this set, you can also easily produce a polynomial that the leading term is not bounded, but the polynomial is bounded. So do remember, it's not such a trivial case as just looking at the leading part of a polynomial. Okay, so I just wanted to also remark, because I also already said that we're going to be interested in n bigger or equal to. Silently, I'm always going to assume that S is bounded. Also, we can remark that the degree with respect to the set is also the same as the degree with respect to the closure of the set, which is also easy to check. So we can also assume that S is closed. What else I wanted to say? Yeah, and of course this degree with respect to a set is always less or equal than the degree, the standard degree of a polynomial. Maybe I'm going to say a few words about previous results. So for instance, most of the results are in R2. Today I'm going to talk about any dimension. So let's say in any dimension we know that if S is a subset of an algebraic set, then the algebra is not finitely generated. It leads to some drastic changes in the behavior between the case of fat and non-fat. So I'm going to assume also here that set is fat. Fat meaning it is contained in closure of interior, meaning there are no thin parts sticking out. Okay, so so still also Plaumann and Scheiderer in dimension 2, they shown that if a set is fat at infinity, this algebra of bounded polynomials is always finitely generated. Whereas a little afterwards, unfortunately, it appeared that this need not be the case in any in higher dimensions, which was a really interesting result, which I'm not going to talk about. Also, there are some effective formula, also in any dimension, but for special cases of the sets by Netzer, by Krug, by myself also. And well, as for, let's say, what's going to be more relevant to the further part of the talk, are two results. That one is by myself and the other is with Kurtyka and Spodzieja. One is, it's in dimension 2. It's related to to a result like this, which I'm not going to talk about again. There is a related problem, closely related, but the relation is not completely understood at the moment. And there is in this related problem, you can reduce the dimensions of sets. So, for example, a set of dimension 2, you can reduce somehow to considering sets of dimension 1. And what I managed to achieve is to do this reduction also in the case of the study of bounded polynomials or of the degree. And this theorem says that if S is any semi-algebraic subset of R2, there exists, so for any such S, there exists a family of testing curves. Let's say a family of testing curves for the degree, gamma C, and gamma C are parameterized by parameters in one less dimensional space, and they have, first of all, fixed number of components. So these are semi-algebraic curves with fixed number of components depending only on S, and parameterized analytically by this parameter C, or maybe I'm going to use U, which is really important. So it means that you have an analytical parameterization of this family of curves by the parameter U. And of course, why are the testing curves? It means that the degree with respect to the set S can be retrieved as the degree with respect to a generic member of the family. Maybe I'm going to put an F here. So if this is still, if it recalls somehow the, well, it is much stronger than, how to call it, Then the standard reduction of quantifier elimination, sorry. It is still much stronger because for fixed degrees of f and a fixed s, you already have the whole family of testing curves, and it's also uniform with respect to any degree of f. So this is one thing, and the other thing is the stability. So this was with Kurtyka, myself, and Spodzieja. If you look at a set SC given by, okay, this was only one thing. If you look at something like this, there exists a finite set V such that for any C in the same connected component, of R minus V, we have that the degree of the sets does not change, with respect to the sets does not change. Meaning that the behavior at infinity of the sets with respect to all the polynomials is, you cannot see the difference between them. And this was also in dimension 2. So I put them here because, like today, what I wanted to say was about the generalization of these theorems to any dimension. In fact, what was really somehow exciting, well, especially with the second theorem, is that in fact this set V here is contained in the bifurcation values of G. The G that describes the set SF. You can think like if bifurcation values of a polynomial are the ones which are not regular values of a polynomial, and regular values, they say that the polynomial next to this regular value is a trivial C infinity fibration. This is what I'm thinking here. If you mean at infinity, it just means that you can do it is going to be a fibration outside a compact set. So, for example, the critical values from only the compact part, they do not contribute to the bifurcation values at infinity. So, this was somehow here. What I wanted to say today is that the theorem here, so this is here is joint work with Vincent Grandjean. So this is myself plus. And well, this theorem here holds, maybe, I'm just going to, yeah, here it was dimension 2, now it's going to be dimension n. We have to assume for this, for any dimension, that S is fat for simplicity. There exists a family of testing curves, so still, these curves are still semi-algebraic curves. U is an open subset of Rk. K is less or equal than n minus 1. Still, they have a fixed number of components. Still, they are parameterized analytically by U, and still, they retrieve the degree of f on the set S. So instead of looking at the set, you just have to look at generic members of a family of curves. So you just look at a curve. And if you choose it randomly, you're going to have exactly the curve that's going to test the degree of f. Do remember that this is symbolic. Like, this is not symbolic, but this is symbolic. Because every curve at infinity can be parameterized, like is an arc, like every part of a curve is an arc, it can be parameterized as a Laurent-Puiseux series. So it means that you just plug in a series into F and you're just looking symbolically at the degree of the highest part that you're left with. That's it. And the theorem 2 I'm going to put maybe here's because it's going to be a bigger generalization of this than just. So we're going to put a C, but this time, like here is just only G1 and in dimension 2. And here we were able to prove that this works only also for any mapping, let's say, K. Maybe K is not good. CL, where G1, GL is a mapping from Rn to RL. And as with this, maybe I'm going to turn back to the black. There exists a finite set, not a finite, of course not, because it's going to be of codimension 1 at most, so not finite, nowhere dense, and nowhere dense semi-algebraic subset V of the values such that, and the rest is the same for any CC prime in the same connected component of RL minus V. The degree does not change with respect to this set. So maybe I said I'm going to do some examples, and now I stopped doing examples. So I'm just going to do the simple, quick one. So the example still, let's say, x, y less or equal 1. The monomial examples are the simplest ones. So let's say here with this example, the testing curves are obviously just x, y equal c, all the reals. And do note, and it can happen, and it might happen, that the testing curves do not need to lie in the set S. It's not a curve selection lemma, no. It might, like here, most of them, like somehow they lie in some sense. But even sometimes they might, like all the testing curves, you might choose them in such a way that none of them, like all of the testing curves have unbound, like do not lie in the set S, in the sense that an unbounded part of them does not lie in the set S. And of course, if we're looking at the stability, you can see that this set is somehow, like the stability says the sets look somehow the same way for most of the values. So if you look at this set, it's just, let's say, I'm going to put, like if you have maybe here C, maybe no, 1, let's say. But now I'm going to look at the set x, y less or equal than C. So if C is less than 0, it's empty. If C is equal 0, it's just a cross. And if C is bigger than 0, it's just this flattened cross. And it looks more or less the same. And in fact, this means that here, well, from this theorem, we know that exactly the degree will not change. So you can think about more complicated examples that somehow the same thing happens, that the degree, it somehow says that the set essentially at infinity is the same. Okay, so maybe I have a moment to say about the proof. Because like the title was the degree and multiplicity with respect to a set, and I haven't said a word about a multiplicity. Okay, so because like in general, I'm being a little lazy because we have even more general theorem here. But I'm being lazy. So let's stick to that. And so I'm going to say, because my time is running off, I'm going to say a couple of words about the proof, and therefore I'm going to say something about the multiplicity. So proof goes more like this. We have to, like, we're doing something at infinity. Usually there are not so, like, there are no, well, no is too hard a word, but there are, like, established methods for infinity are not so established usually. So we're going to do something, well, something trivial, meaning we're going to localize the infinity. So we're going to localize. We're going to solve a dual problem and then go back. And the dual problem is the multiplicity. Meaning that, well, how do we localize maybe first? We're going to just look at the inversion. Nope, not this one. We're going to just look at the inversion. Sending x to x over x squared. This is a well-defined everywhere or Rn minus 0, and it sends 0 to infinity. And it also does not meddle with the, like, everywhere outside 0, it's a diffeomorphism. It does not meddle with the topology of the set. And so, instead of looking at the degree at infinity, after doing this, we just need to look at the multiplicity at 0 of the polynomial. So, in fact, like, if we do the inversion, if we use it to a polynomial, let's say f of the inversion, it's going to be just like 2 times the normal degree of f times a polynomial. So we have, after inversion, we have the duality between the degree of f with respect to the set S is 2 degree f minus multiplicity of the inverse S of the inverse f. Let's say, let's define this as the inverse f. And the multiplicity, well, I don't have the definition here, but as you might suspect, the multiplicity with respect to a set is just defined as the multiplicity, like if you have the definition with respect to the curves at point 0, then the multiplicity with respect to the set means that we are just detecting it with respect to the curves that lie inside the set S. So it's just, let's say, a generalization in some sense of the standard definition of the multiplicity. So what happens here, like let's say originally with in dimension 2, the proof of the theorem was much easier because you have a simple, somehow you have the resolution of the set and like resolutions in dimension 2. It's somehow like resolving curves and it's kind of simple. So you know how the set behaves at infinity easily. And here, let's say in any dimension, we have to somehow assume, for example, the fatness here, because we are not, well, we have to somehow, well, we have to use the resolution in general. And in fact, we use embedded resolution for this. So maybe I'm going to really simplify this to fit in the time. So this is a gross simplification. So after we look at this, we do the localization, meaning we inverted the set. Since we were interested in an unbounded set, it means that our set touches 0. So let's say this is our set S, and this is 0 or infinity, whatever you please. And then you just try to resolve it so that on every, let's say you might do the full resolution, embedded resolution, so that all the traces of the set S on the exceptional divisors are fat, in the sense that they don't have any fin components. So when you look, let's say, on the exceptional divisors on the trace of the set S, this is not a good picture, but this is, as I said, a very gross simplification now. So when you're moving the parameters C here, it means somehow, do remember that after inversion it's going to mean that there is the inverted G, there's C1 times an appropriate power of the norm. If you move the C, it means that you move inside, you move the set, it's going to be bigger or smaller. So let's say it becomes smaller. And the only thing you have to really so you have to check that when it disappears, that it does not disappear along, does not have this tendency to disappear along something which is not fat. Like, for example, being smaller, like on a segment, that it cannot happen. And you have to be careful when it disappears from some of the divisors. And this is how you retrieve somehow this nowhere dense semi-algebraic subset. These are the values that you have the disappearance from the exceptional divisors of the trace of every component of the set S. And this is in fact exactly the generalization how it was happening in dimension 2. Only any dimension here. Okay, I think, let's say I said what multiplicity is, I said a couple of words about the proof, and I think I'm running out of time, so, well, if there are any questions about applications, I can say something about that, but after my time. So thank you very much.
Yeah, thank you.
You're welcome.
Other questions, comments, remarks? Yes, please.
Maria, I have been this picture.
This one?
Yes. In some talks about Lipschitz embedding, it look like the pizzas that Valencia and Alexander are working a long time ago. Do you know how are they related?
I somehow know, but this is not something to say in 2 sentences, or I'm unable to at the moment. But this is why I started working with Vincent about this, because he gave a talk about the pizzas, and I told him, like, but hey, in dimension 2, it's exactly what I'm doing. So yeah, this is somehow let's say, I do not think that the result, that the degree is connected to the Lipschitz, let's say Lipschitzness somehow at infinity. But I do think the methods are similar. So I don't think there is a direct connection, let's say a direct connection as a theorem between their pizza, yeah, there won't be so simple a connection, because even here in there are certain, like, you could, for example, there can happen that the degree does not change, but the number of components at infinity changes. Only somehow there is the complex structure that comes into this, that somehow, you know, you have a new pair of things that appear in the real part. But let's say analytically they are still the same. And they do not influence the degree. So, but from the point of view of being like in the same class of Lipschitz, of Lipschitz equivalence of sets, for example, these are going to be different sets. So.
Other questions? Yes?
Just a comment. Last week in Montreal, Alexandre Fernandez in his talk He mentioned that the question whether the degree and order of history are or not invariant, Lipschitz invariant at infinite.
Yes, because like this is in this sense, yeah, because like I was referring here to the stability with respect to the set. So in this sense that, well, so I said it's one way, but it does not necessarily be the other way. So in this sense, yes. So this question is still open.
Further questions? No? Okay, if this is not the case, then I want to have your attention for one more announcement before this is over. Ah, okay. Then we I would have done it afterwards, but okay. One more announcement.
Okay, this is for tomorrow's dinner. It will be in Restaurante Arroyo, that means Creek, I think. It will be very near your hotel. The bus will depart from the hotel 7:20 p.m. and the return will be by yourselves by taxi. It will cost 500 Mexican pesos, and please take Mexican pesos.
How much?
500.
500.
The taxi?
The tax.
The taxi tickets, it wouldn't be very expensive. Don't worry, but the restaurant has to provide a secure taxi. That will be even more expensive, but it will be more secure. That's my point. Please, tomorrow will be a version outside, and maybe you can confirm if you would like to depart with all of us in the restaurant to make it accomplish. And an email will be sent to you with more details. Thank you very much. Thank you to the speaker again.
Can you quickly check if this is correct what I wrote there?